The next part is to design a gravity retaining wall for the earth pressures that you have already calculated. And the way that we are going to do this is that we are going to look at 4 different cases. So I'll have case 1 where the wall is sitting at the ground surface at 0. So it's 30 feet high, but the wall is simply sitting at the ground surface, and what we want to do is find the width B for that wall. And then case 2 is going to be with the wall embedded 5 feet. So it's still at 30 feet at the top, but it's 5 feet below the ground surface, so the total wall vertical is 35 feet. And again, we want to find the width B for that particular case. That's case 2. Case 3, we go down to 10 feet below the ground surface, and again, we want to find B. Now remember, the water table is at minus 5 feet. So when I put the wall down 10 feet, I'm going to be 5 feet below the water table. And then case 4, oops, I'm going to do that one for you, but case 4 is we're down 15 feet, and again, the water table's at 5 feet, which means in this particular case, we're 10 feet below the water table. In a sense, you're going to do these 4 cases. I am going to show you how to do case 3. So, you can, that's the way I'm going to guide you through this. I'm going to lay this out, and what we have is you need to fill out a number of tables. So, in other words, I've got a table here for the active and passive pressures and the water stress, and then we're going to calculate the areas, and then the moment arms, and then we're going to do the factor of safety. So I've laid it out so that your work is organized, so I've helped you out in this particular sense. And then, in the end, you're going to get your B's, and that's going to be your answer. So let me go to case number 3, and I'm going to do the solution for you, and then you can use this as a guide for doing the other cases. So this is case 3. The depth of the wall embedment is 10 feet. And what I'm showing here, I'm showing the diagram for you in a sense. So like I said, I've helped you out a little bit. I'm using this, so it's these symbols, so that, the square means the line number, because we've been talking about line numbers here. The circle is the area number. So in other words, this is a line number. These are all line numbers. And these are all area numbers. Okay. So you've previously developed the equations for line numbers 2 and line numbers 3. We're going to use those now. And so we have the active zone here, we have the passive zone here, and then underneath, where we got the weight of the wall, and then underneath we have the water pressure. In this case, we have a water pressure because we're 10 feet down and the water table's at 5 feet down. So we have water pressure due to that extra, 10 minus 5 is 5 feet. So let's look at how you can determine exactly what these diagrams are and then come up with the area. So the one thing that I've given you at this point, we know that this is 1200 PSF. So in other words, this point right there is 1200 PSF. We got that from previously. Now, what I want to do is I want to use line number 2 and line number 3 to get this value here and this value here. So you develop the equation for the line numbers, and so remember my coordinate system is such that this is y equals 0. Y equals 0 is here, and I want my x value. So here my y value is -10, so I put in y of -10 to get these 2 points. For the active region, line number 2 gives me, when I put in -10, I'm going to get, in other words, I put y equals -10 there, I solve for x, I get x equals 1845. So that gives me that number there. For the passive zone, I'm using line number 3. Line number 3, we developed this equation for line number 3. Again, I put -10 in here. I solve for x, I get -3534. So that means that this value here is 3534. For my water pressure, well, I'm 5 feet below the water table, so the depth below the water table is 5, 62.4, the density of water, so 5 times 62.4 gives me 312, and that gives me this value here of 312 psf. So now since I now have everything, that's 0, that's 1200, that's 1845. That's 0, that's 3534, there's 312. So I have enough information now to calculate all of the areas, 1, 2, 3, 4, and 5. So now that we have that, let's start calculating those. Well, 1 is a triangle, right? So it's going to be 1/2 the base times the height. And so it's, this distance is 30 feet. And then I have the 1200, so it's going to be 1/2 times 30 times 1200. That gives me 18,000. Two is a rectangle. Well, this distance is 10 feet. This is 1200, so the area of that rectangle is simply going to be 10 times 1200, 12,000. Three is a triangle. So it's going to be 1/2 the base times the height. Again, the vertical distance for 3 is 10 feet. And the horizontal is going to be 1845 minus 1200. So it's going to be 1/2 1845 minus 1200 times 10. 3225. 4 is here. Again, it's a triangle, so it's 1/2 the base times the height. The vertical is 10. The horizontal is 3534. So it's going to be 1/2 times 3534 times 10. 17,670. 5, we got the 312 there. 312 there. Now, here's where it becomes slightly tricky, is the width is b. So to get the area of 5, it's going to be the width b times the 312. So it's going to be 312 times b, which I just simply put there. The weight of the wall, now we're going to use that concrete is 150 pounds per cubic foot. So gamma concrete equals 150 pounds per cubic foot. So what I need to do is get the volume of this concrete here. It's going to be, the vertical is 40 feet, the horizontal is B, and perpendicular to the paper is 1 foot. So I guess I didn't even write the 1 foot. So it's going to be, so to get the weight of the concrete, we're going to have 40 times B times 1 foot perpendicular to the paper times 150 pounds per cubic foot. That gives me 6,000 B. Then the friction here is what? I've got the, I have to figure out what is this component here. In other words, I have to have vertical equilibrium right here. I have to have vertical equilibrium, so this is going down. This area points upward because it's water pressure going upward, and this is going upward. So to get this one, I'm going to simply take, to keep equilibrium, it's simply the weight, W, minus the area of 5. So I simply take the weight, area of 5, or I guess this, yeah, do it this way. The weight minus the area of 5, and then the coefficient of friction is given to be 0.35. So it's going to be 6,000 B minus the 312 B times the coefficient of friction mu, which is 0.35. Multiply that all out and I get 1991 B. To get the moment arm, so now we need moment arms. Well, what point? We're taking moments about this point, remember? So we've got the active zone here, we got the passive zone there, and of course, what are we looking? We're expecting the wall to rotate about that point. So it's going to rotate like that. There's my moment going like that. So I'm taking moments about this point here. So I want the moment arm for those areas, which means what? Well, so I'm measuring, I have to find the centroid of the triangle. So I got a centroid for this triangle, I got a centroid for that rectangle, centroid for that triangle, centroid for that triangle, a centroid for that rectangle, and then of course I have this W, which is the centroid of the rectangle, that rectangle, and then this W, which counteracts the other. Or sorry, well, we actually don't use this one because what we're assuming is that the wall lifts off just a little bit, enough to lose contact here, so we don't have that one. So there's no moment arm associated with that one. That one disappears, but the water still remains. So it's the centroid of that rectangle for that water. So I don't want to, you can all do this. So what do I know? The centroid for that triangle is what? It's 1/3. I go up 1/3. That distance is going to be 1/3 of 30, 1/3 of the total, which is 10. And then I also have the 10 here. So the moment arm for 1 is 20. For this rectangle, that total distance is 10. For rectangle, it's half of that. So 1/2 of 10 is 5. So the moment arm for that is 5. For this one here, it's going to be 1/3 of 5. One third of 5 is that looks like it's a mistake there. Whoops. That should be 1.67. And then similarly, this should be 1 point. So there's a little mistake here, but I'm just going to tell you, okay, you're going to have to redo some of the numbers, but that should be 1.67 there. And oh, sorry, no, it's not. It's not. This is actually correct. 3.33, because it's not 1/3 of 5, it's 1/3 of 10. Okay. So because this total distance is 10, that's certain where I got the 5 from. So those numbers are correct. You don't need to redo anything. So that's 3.33. Then the moment arm for this one, I'm taking moments about this point. So the moment arm for 5 is what? Well, the center here, because it's a rectangle, the width is b, so it's going to be b over 2. And similarly for the W is going to be b over 2 also, because it's because the wall is, we're assuming, a rectangular shape for this, just to keep things simple. And then we don't have a moment arm for the friction. Okay. So now we need to, so we have all of this filled out. We have our areas, we have our moment arms. So now we can do our factor of safety calculation. And the resisting the resisting force is what? Well, for the resisting force for sliding, so this is sliding, resisting force. So we're evaluating sliding, which means we don't need to do the moment arms. What resists the sliding? Well, it's this passive zone and the friction. So I simply add those two together. So I take my friction and then the passive zone, which is 4, add those together. That gives me my resisting force. So I'm just going to leave it like that for the time being. Notice it has the unknown B in it, but that's okay. The sliding force is what? Well, what propels the sliding? It's going to be all of these actives, the 1, the 2, the 3. And so that's going to be 1, 2, and 3. So 18,000. 2 is 12,000. 3, 3225. I add those all together and I get this. Now we're given that we have to use a factor of safety of 1.5, so what do? So remember that the factor of safety, F, S, is going to be the resisting force over the sliding force, and that's 1.5. So I take this, put it here. I take this, I put it there. I use the 1.5, and I solve for B. Okay, the only unknown there is this B right here. I solve for that B, and I get 16.15 for that B. That means the wall needs to be a width of 16.15 to resist sliding so that it doesn't move. For the moment, factor of safety, I have to find the resisting moment. Well, what's the resisting moment? So again, I'm taking moments about this particular point here. What resists overturning is this passive zone and the weight. So it's a gravity wall. Like I say, the weight The weight creates the friction, the weight resists overturning, and that's why we call it a gravity wall. So I have the 4, I take the area times the moment arm, goes here. Then the weight times the moment arm goes there. That gives me my resisting moment. And then the overturning moment is what? Well, what overturns it? Well, 1, 2, 3, and 5. So I have 18,000 times 2 goes there. 12,000 times 5 goes there. 3225 times 3.33 goes here. And then 5, 312 times b over 2 goes there. That is my overturning moment. And again, the factor of safety for this is going to be m resisting over m overturning. And the factor of safety, again, we're taking as being 1.5. That's there. That's given. We set that in advance. Oops. And then what do? Well, I simply take this equation here. I put it here. Take this equation here. You can simplify that a little bit. Put it there. With this 1.5, I then solve for b. So there's a b here, and there's b squared here, so it's a little bit more complicated, but you can solve for that. I solve for b, and I get 14.57. So to resist overturning, I only need 14.57. To resist sliding, I need 16.15. So which one is more? I have to build this one to be safe for both sliding and overturning. I have to be the bigger one. So that when you get to the last page here, you want to fill in this table. So here are the 4 cases drawn out, but all you need to do is fill in this table here. And I filled it in for case 3. We're at -10 for the base of the wall. The sliding B is 16.15. The overturning B is 14.57. I have to choose the larger of the two to put there. And then what you want, so now I know the B. Okay, so my wall for case 3, is what? It's 40, this is 40 feet, and this distance is 16.15 feet. And then we're taking 1 foot perpendicular to the paper, so the concrete volume, which is what we want to compute, we're looking for the lowest concrete volume. Very simple way to decide which wall to choose. It's really more complicated than that, but for the sake of this project, I just want you to use the one that has the lowest concrete volume. And so I get 40 times 16.15 times 1. We have 646 cubic feet of concrete for this one. So what you are going to do is you are going to do all the other depths, so 0, -5, -15. Put the concrete volume for these, and then you choose the lowest one. And that will be the one that you recommend to be built. The lowest concrete volume. So of these 4 cases, choose the lowest concrete volume. Okay. that is the instructions for this part of the project.